The third important parameter for a cache design is the associativity of the cache. Let's first look at this access pattern example. So as we said before, we may have some spatial locality and we have some temporal locality explored in this access pattern. And I said that this could, for example, be from the inner loop of an application ABC A+1, BC A+2, BC, and so on. And this works well in a cache where you can explore the temporal locality as well as spatial locality. However, what would happen if we were unlucky? What would happen if Murphy was involved and Murphy made sure that both the address B and address C index to the same cache location, index to the same cache set, had the same values of their index bit? Well, that means we will get conflict misses, big time conflict misses. And the potential performance loss you would get if you're unlucky and they happen to map to the same index value is maybe 10 or even 100x performance degradation. So this could be very severe, and the performance of such a design would not be very stable. So we need to do something about this. So what we want to do really is to increase the associativity of the cache. And increasing the associativity is the same thing as if you allow more than one name in your address book. So let's say that you allow 2 names per page in your address book. That means that both Tommy and Thomas telephone numbers could reside in this cache at the same time. And even though you had both Thomas and Tommy were a very close friend of yours, you still wouldn't get lots of misses in your address books because you will avoid those conflict misses. So this is the way we would like to improve our cache designs as well, allowing more than one data item to be stored associated with the same index function. So here you have such a cache design, and just looking at the design parameters here, it's a 1 megabyte cache. It's a 2-way set associative cache, and its cache line size in this example is 4 bytes. So in this example, we're only storing 1 word per entry, as we did in some of the very previous, very first cache designs we discussed. Okay, so we have 2 bits here that identifies a byte within the word, the 2 ones here. So they're going to toss over our shoulder. We're going to have 128k sets because we're going to store 4 bytes and 4 bytes. So it's a total of 8 bytes per set. Okay. So in this example, we're going to call this a set. So whatever entries in the cache that is uniquely identified by the index is our set. So we have 128 kilo entries or 128 kilo sets. And in order for us to uniquely identify the correct set that we're interested in, we need 17 bits of the address. That's going to be the next 17 bits. So now we have one cache line that's identified to the left and one cache line identified to the right. We have a multiplexer at the bottom, and the job of the multiplexer is to choose lefty or righty. The question is, how should this select signal be produced? Okay, we need a single bit that chooses left or right, but how can we know which one to choose? And that's the next question to you to figure out. Should we use the MSB part? Should we use some of the LSB parts of an address? Or do we have to look at both address tags to determine left or right? And that's exactly what we need to do. We have to look at the address tag to determine that. So the design looks a little more messy now. It's a design where we have 2 comparators, one comparing lefty, the address tag of lefty, and one comparing the address tag of righty. And then we have some kind of logic. I haven't really put all the gates here, but you can probably imagine fairly simple design that would have that would produce the right select signal as well as producing the hit signal. The access time here now differs a little bit because you see, first we have to try the index function to get the address tags out. We have to do the comparisons, we have to do the logic, and then we do the select signal. When we only had large cache lines, then the select signal was taken from some of the address bit that is available to us right at the beginning of time. But now we have to wait until both comparisons are done and the logic has done its job before we know the select signal. So potentially the access time here could be slightly longer than for the other cache designs we've seen, because we need to add the logic as well as the latency from the provide the correct select signal until you have the correct output from the mux. So pros and cons of associativity, associative caches, set associative caches is a common name as well, is that they avoid conflict misses. But the negative thing is that you potentially could get a longer access time. The implementation can also be a lot more complex. You have to have the comparators, you have to have the muxes, you have to have a wider SRAM implementation, and that could also be costly for you. And since you're reading out, you're going to read out the cache line and the address tag, both of the left and the right cache line. That means you're going to read out twice as much data as you really need from the cache compared with the previous designs, which means that the power consumption, what's called the dynamic power consumption, is going to be higher in this design. If you like to combine the associativity with a larger cache line, you may have a design that looks like this. So here we have a 1 megabyte cache. It's a two-way set associative cache. The cache line size in this example is 16 bytes, and a word is 4 bytes. Okay, so that means that we're reading out 16 bytes here, 128 bits, but we're only going to give 4 bytes back to the processor. That means that we have to do some 4-way multiplexing of the data that comes out, and we also have to do one-way multiplexing, two-way multiplexing to choose lefty or righty. So this is how it works. We're going to have one select signal coming from the logic here that compares both the address tags, and that's going to give you part of the information, and two of the select signals are going to come from these address bit that uniquely identifies a word within a cache line. So 2 bits plus these bits are being inputted to this mux, which is an 8-to-1 mux, which will do double job. It will choose left or right, but they will also, within the cache line, left or right, it's also going to choose the very word that was requested by the processor at that point in time. Finally, I'm also going to talk about an extreme way of doing this, doing associativity. So far I've showed you in both these examples a two-way set associative cache. They could also be in a 4-way set associative cache or an 8-way set associative cache. And that number, 4-way set associative cache means that there are 4 possible places where each cache line can reside in the cache, or 8-way, consequently 8-way. So the width of this SRAM increases the more associativity there is. The more data you read out, producing dynamic energy, increases with associativity as well. And one extreme design point is it's what's called a fully associative cache. So in a fully associative cache, in some sense, you have a null index function. And all the data you can fit in the cache can be in any of the possible places in this cache. So in this design example, in 1 megabyte fully associative cache with a cache line size of 16 bytes, you would have 64K cache lines with a null index function. That means that you will actually need 64K comparators as well. You would need to read out 64K address tags and so on. And this very wide logic that has to produce a select signal of 16 with 16 select bits, because you will need to do a 64K selection as well as these 2 extra bits to read the right word from the cache line. So this clearly is an impractical design. Nevertheless, we will discuss several ways of implementing fully associative caches in this course, where we actually down the road will be able to implement fully associative caches without the need of having a single of these comparators implemented in hardware, but more about that later. So for now, fully associative cache, what this is sometimes called a CAM as well, is indeed used for smaller caches, because then, if you only have a handful, maybe 100 entries, maybe you can afford to have those 100 comparators. And it's used, for example, in a kind of cache called translation look-aside buffer that we're going to talk about later. Fairly common there. It's also used as a contents addressable memory. So this is the content addressable memory, is sort of like a fully associative cache, and where you can store both key and data. And this is often used, for example, in routers and so on, because you can do an associative lookup and you can get the routing function right away from these kind of caches.